now if you speak, you see that you have your microphone working there. So
Okay.
can you just refresh?
This is play 5.
No.
This is not the 4.
Yeah, there you
Okay.
go. So you see, and if you put hello,
Yeah.
so there you go.
So for the
And
break.
now you can put at so you can stop everything.
Yeah.
trying not to to allow it to block. So the assignment in this block will be 1 day.
I saw that and I was really
You downloaded the slides?
Yeah.
Okay. Yeah. So maybe there are 4 lessons. In each lesson, today we will learn how to model, and in each lesson we will learn something: how to use operational laws, how to use a tool, and how to do it in UML. And then there will be a short question about each part.
Is it like an online exam, the assignment? Or?
Submit a PDF, but we will publish it at midnight of Tuesday and close at midnight of Wednesday.
Okay.
So if you start there and you have not studied, maybe you have problems to do it in 24 hours. Well, maybe you cannot dedicate 24 hours. But if you have studied before the exercises and the examples we see in the lessons, 1 hour estimated time. So I plan to publish also the assignment, last year assignment, that was for between 2 hours and a half or 3 hours of work, and they had a week. Well,
Wait, 1 week of just studying the material, or 1 week of preparing the assignment?
they had 1 week.
And we are online now. Okay. Time to start. A moment. Online people, can you hear me well? Camilla? Hello? Yeah, okay, thank you. So welcome to the block on performance evaluation in the course 2DB 608, software design. This block consists of 4 lessons and an assignment. My name is Diego Pérez, and I work the Department of Computer Science and Media Technology. If you want to contact me, the primary way is the email. It's the one I more or less continuously check, and it's diego.perez@lnu.si. So today we see the first lesson of the block, performance modeling. After this block, first of all, I want to clarify the assignment. On Wednesday in 2 weeks, so the 4th of March, we will have the assignment. There will be like 1 day assignment. It will be published in the beginning of Wednesday, and the deadline will be 23:59, the same Wednesday. The estimated work time for the assignment, if you have already studied what we have seen during the 4 lessons, will be like 1 hour. Yeah. So if you know how to do everything, in 1 hour you can complete everything. So the assignment will be a practical exercise where you apply what we see during these 4 lessons. So today, with the performance modeling we are going to see, you will be able to do already like 20% of the assignment. So we study before the assignment. You arrive with the clear ideas of how to solve the problem, but once the problem is released, it will be short. So if you have studied it in 1 hour, you should be able to complete it. Yeah.
Yeah, I think it's easiest. We grab this one, making a hole there. Yeah, there's a.
This?
Yeah, sorry. It's easier not to see.
Better?
There was like a light spot because of the.
Ah, okay.
On the wall.
Okay. Thank you. So why we are doing this performance evaluation? The goal of performance modeling and analysis. So today's systems are expected to have a lot of good properties, like to be powerful, highly available, scalable, well-performing, green, cheap, open, secure at the same time. So designing a system that satisfies all these properties, it's very difficult. Even if we have already a running system and we want to do some upgrade, it's difficult to know if the upgrade will satisfy these properties. And even if we have a running system, it's also difficult to measure the properties. So for the availability or reliability, how much does it fail? So you will need to measure a lot of time. You cannot look at the system for a short period and say something about its percentage of availability. So knowing these functional, non-functional properties, availability, reliability, performance, it's difficult. So in this block of the course, we will study performance modeling analysis, and its goal is to provide the modeling principles and simple mathematical laws to characterize and evaluate the performance of computing systems. So we will not be able to say things about the reliability of how green it is or the cost, but about performance. If it is fast enough or not, we will be able to say something. And software design at design time, so without needing to develop the system and then maybe say that we have failed. So this knowledge on performance can be used during system design and system evolution. For instance, to size the computer infrastructure. We have a piece of software that we are required to install in an organization, and we know that it has some application servers, some database. The application server, should we put a load balancer? Is one server enough? Should we distribute the load? If we distribute the load among how many? 2, 3, 4? Each one that we add will be better for the performance, but worse for the cost. We are for the yeah. So this is the problem of sizing a computing infrastructure. The scalability, if we have a computing system, an application that is now serving Vejo clients and we want to open to the world, if now we are having like 10 users per minute and we want to allow everybody, it's like, can we see if before opening and maybe crashing, can we see if our application is scalable? If suddenly 100 users per minute arrive. We can also evaluate different design alternatives and predict the performance of both and choose the one that is more convenient. So this an example is if some part of our system is a database, can we implement a centralized database that is more common and easy to install and maintain? Or if this will not give enough speed, we have to maybe to think about implementing a more complex database distributed that can handle more users. So before deciding if we invest this effort in a distributed database, we can think if we need it or if a centralized would be enough. Another point where we can use the performance evaluation we do at design time is to renegotiate the requirements. So up to now you have seen requirements engineering. So maybe the user says, I want my web application almost in real time, so the users don't feel any most latency. So there are studies that say that below 0.2 seconds the user thinks that there is no delay. So I want my application below 0.2 seconds, and you wrote in the requirements 0.2. And then there are other requirements. And on that phase, you annotate it, and you did the requirement engineering. Now you start designing the system, and you do some performance evaluation about the possibilities you have, and you see that you cannot answer in 0.2. So that the minimum is 0.3 or 35. So you can go to the client still at design time, so early after the requirements, and say, look, this is what we agreed or what we elicit. It's not possible to do it with this budget. So either we can increase the budget or we can relax the requirements. Maybe you need only some latency for some special users or for some special part of the system, and other queries can have lower priority and be slower. So we can refine the requirements soon after we have set them. So we don't set the requirements, we develop the system, then we realize that it doesn't work, and 6 months after the requirements have been written, you say, I cannot. And we can also get insight about the limits of the system. So if we have now a system that is working well, but we don't know in which percentage of its capability it is. So it's like it's almost near saturation. If somebody does a couple of requests more, everything will crash, will collapse, or it's working well and it accepts some variation. So these are the things that with a performance evaluation we can answer. So this is another example with what we are going to work. So if we have a client-server system, so here is the client and uses a browser to access a server that has a web container, which communicates with some Java beans and which communicates with the database to answer the client. could we say what is the application response time for the client? So when the client communicates, it's like, is the answer going to arrive in average below 1 second, 2 seconds? What is the resource utilization? Are these containers, the server, like 100% of utilization, creating bottlenecks or not? Can we work with a single centralized database, or do we need to invest effort in a distributed database? So with this information, we cannot say much of this. So we will learn what else we need, and the techniques to answer this kind of questions. And we will do it through models. So we will create other models that allow this performance evaluation. And we will use the queuing network language, queuing network models. This is one of these. If this picture is familiar to you, you know what these circles represent. More or less the second hour of the lesson you could skip. And if not, this is the language we are going to use, and I will explain after the break. Queuing, queue, like line, one after the other. Queuing. So this is a server, and this will be the queue. But for the it's a mathematical model. Can be done with many tools. Then we will see one tool in the third lesson of the block. So far, the first and second diagrams drawn by hand. And then in the third lesson, we will see a tool. So let's see some definitions about the computer performance. So it means that there is more than one. The first, the computer performance is the total effectiveness of a computer system, including the throughput, individual response time, and availability. So this definition is very nice for the users of the system. I want low response time, I want a lot of availability, I want throughput. And the second definition is the computer performance is characterized by the amount of useful work accomplished by a computer system or computing network compared to the time and resource used. So this view is useful for the system managers. So if they want to do a lot of work using few resources. An example, if we remove the computer, so performance only, system performance. If you go to the supermarket, we would like to, when we go to pay, to have a lot of cashiers and all open. So we want to go there and find somebody who is idle for us. So in that case, we will have a response time quite good and availability, because there will be more or less at any point there will be somebody available for us. As clients, as the owner of the supermarket, they want to use as less cashiers as possible to still satisfy the work for the users without making them too angry for waiting. So two views of performance from the client side and from the system administration. So a lot of work with few resources. Some metrics on indices of performance that we are going to work with: response time of an application, the throughput of a resource utilization. These are the three most common, and we will explain one by one in the next slides. And then other examples are lost rate of messages on a communication channel, so through the Ethernet, the bandwidth utilization of a wireless channel, or a blocking probability of a channel. So with the three first, response time. We define response time as the total amount of time the system takes to respond to a request for service. So in this example, if there is a client here and this is a server on the internet and it makes a request, the response time will be the time since this makes the request, so traveling, the server will execute it when it can, because maybe it's busy in the moment when it makes the request, and coming back. So the response time is the sum of these three concepts: the service time, how long it takes the server to do the work that the client has asked it, the waiting time, how long the request from the client had to wait in the queue of the server before it started the service time, because the server was busy doing other things, and the transmission time, how long it took to move the request from the client to the server and from the server to the client. And from this, it starts to be more similar to a queuing network. So we have a server that will have the service time, the client that sends something to the network, and it will have some delay. It will wait in a buffer until the server can handle their client request, and then there will be another delay time. So transmission time twice, waiting time, service time. The second index, the throughput, the rate of production or the rate at which something can be processed. So how many clients can we serve per second, for instance? Or in a car factory, how many cars we produce in a day? How many cars we produce in a year? So this is independent of the response time, because maybe one car, since it starts in the plant, it takes a lot of time to go out, but the plant is creating cars quite fast. The production rate is high. So instead of cars per year in our systems, we will be like requests per second or jobs per second. We are not working in the year time frame. And resource utilization, the proportion of time in which our resource is used. And the rest of the time is when the resource is idle. So this 70% of the CPU. Resource utilization 0.7, idle 0.3. So performance, there are several performance interests that they are similar to the two definitions we have seen before. So from the users want to optimize the response time, the throughput, minimize the blocking probability of the system, while the system manager want to optimize the use of resources. I'm not going to pay for 10 CPUs if I can do the same work with 2. So they want to increase the resource utilization. They are not paying for having something idle, but not too high, because if it is too high, users become angry because they have to wait also too much. So they reduce the idle time and reduce the failures of the system. So with these definitions, interest and metrics, how to evaluate the performance of a software system, there are two families of techniques, based on measurements in the system and based on the utilization of models. If we follow the measurement base, short introduction to the measurement base, we can directly measure the system, we can benchmark the system with different workloads, or we can build a prototype of the system and see and measure how it behaves. So this measurement through experimental evaluation is always useful, it's accurate, sometimes it's required to prove something in the system that is working, and sometimes it's the approach of choice. So if you have the system already working and the modification is minor and you can afford doing these modifications, so it's not critical, and you can obtain the measurement data of the performance, this is very accurate because you are trying in the actual system. But if it's not this ideal case, if we have to build a prototype or if we have to stop the system as it is working now to do these measurements for performance in another situation, it's very expensive and sometimes prohibitively expensive. Another drawback is that if we experiment in the real system, we get very accurate information about one concrete situation, the configuration of the system. And we cannot generalize, maybe, too much. So we have very accurate information about something very concrete as well. So the cons of the accuracy is that it is laborious, and it is not flexible. It may be disruptive. So if we are the software that controls the train traffic, and we want to try what is the limit, we may break the software that is controlling actually the trains. And it can be dangerous. So it's like just to see how much it scales, how many trains we can put, we stress the system, we break the system, and now what are we going to with the trains today? So sometimes it's not the best choice to try in the real system. So the other family is the model-based. That is the one we are going to do in this course. If we are using models, we are not experimenting in the real system. So maybe the real system does not even exist because we are still designing it. So we create a model as much accurate as the system, as much as we can. We evaluate the performance in the model, and then we extrapolate what we have seen from the model, the response time, the throughput, to what will happen in the system. So since the system does not exist yet, we can make this step at design time. So we elicit the requirements, we are starting to design the system, and while we'll design the system, we can evaluate the performance using models. And for the model base, we have three ways, well, two ways and the combination, analytical and numerical, or simulation of models. And we explain more in detail each one. The analytical and numerical techniques are both based on the application of mathematics. So the model is converted to a set of equations, and the performance indices, the response time, the throughput, the resource utilization are computed by solving these equations. If the equations can be solved in closed form, this is analytical method. If the equations cannot be solved and we need to approximate with some numerical techniques, so it's called numerical method. Some examples of analytical techniques. There is a law that we will see all these laws on Friday, that says that the average utilization of a service is equal to the product of the throughput of the system and the average demand of the service. And it's called utilization law. We will see this in more detail on Friday, but now an example. So like we see that the utilization is the product of the throughput that we call X and the demand equation that we can solve, so we can multiply and divide easily. So when can we use this law and this analytical technique? When a case of this example, a computer executes a certain task every 2 seconds, and the task needs half second of CPU. What is the utilization of the CPU? So we say executes a certain task every 2 seconds. So the productivity, the throughput, the productivity of the system is half task every second, so half, and the demand is 0.5 seconds, 0.5 times 0.5, the utilization is 0.25. And another law, famous law, Andal's law, don't know if you have heard about this. It relates the speed up of a system if we increase some part of the resources or if we add more resources. You can, if you have not heard about this before, it's nice to have a look at the Wikipedia. So, yeah. Or maybe there are two.
No, I did the course in physics and music.
Okay. Good. Okay, instead of analytical, we use the simulation. If we simulate a model, the results will be based on the reproduction of traces of the model. And a trace is a possible sequence of events that characterize one possible evolution of the model. So using simulation, we compute a large number of traces, and then we use some statistics, probabilities, and other statistic techniques to compute the performance, the average performance indices. So the accuracy of the results in this case, if we use simulation, depends on the number of traces we have simulated. The more traces, the more precise the results would be, but the more traces, the more time we have to wait until we have them. So an example, if these were the states of the system, from this state it can go here, here, or here, and from this can go here, here. We create a model that represents the states. We execute, and a trace says that the system can pass from this state here, 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 and it did like this, and then like this. We have one trace of how the system evolves. We execute again, and we have another trace. We execute again, we have another trace. We execute many times, and we can see what is the average behavior and get some performance metrics. So if we are using model-based evaluation, analysis of simulation, if we use an analytical approach, we characterize all the possible traces at the same time. We are not going one by one. So it would be the most precise method and the most efficient. It's very fast and very precise. Sometimes we cannot use the analysis because there are not enough mathematics to analyze everything. So the mathematics are still under development. So if we don't have analysis technique, we will simulate the system. So we will start executing samples, and we will use statistics to give performance indices from the amount of the collection of samples we have collected. So the two families, measurement-based and model-based. Sometimes we can combine. If we are, this example is of a system upgrade. We have a running system, and we are requested to do an upgrade, to add some logging server or another database or something. And we need to offer good performance. So before developing and deploying, we do the performance evaluation. So we'll project a system, we will design it, and we will create the model, the performance model. The performance model needs some parameters about the demand or how the system is working now. So we can observe the existing system, we measure it, we give some accurate parameters then to the model we have created before, and for the remaining part, we can evaluate what we can afford in this remaining part. So if we see that the system now, the response time is 0.5 seconds, our limit is 0.75 seconds, and we have to add something else, we can create a model of what is working now, and so we can see what else we can afford, how fast we have to do the other part. So now, to create the model, we will use the queuing network models. This is the model language we are going to use in this block for performance evaluation. Queuing network models are evaluated using queuing theory. This is the theory behind what happens when you have a lot of jobs, scarce resources, and very long queues and delays. We can apply queuing theory every time that there are queues, and this queuing theory is built on an area of mathematics that is called stochastic modeling and analysis. These queuing networks are used quite often in computer systems because in computer systems we see many times this queuing behavior. So in the queue of web request is the web server that wait to be served, the previous example. The queue of a router that is serving from incoming points and transmitting to packets. Databases have logs, so when several writes arrive at the same time, they have to one write has to wait until the other has complete. So this queuing behavior happens in computer systems, and that's why the queuing networks are quite often used for the performance evaluation of computing systems. Now we can have a 10 minutes break, because the rest of the lesson we will explain queuing networks, the language. Okay? So it's 47 now. 10 minutes is okay? Okay, so at 57, we come back. Any question in Slack? No? Okay. Thank you very much. So we can start the second half of the lesson, and now we are going to learn the queuing networks language. And we will, part of the assignment will be create a queuing network, because we will have a description of a problem, and we will be asking some performance metrics like response time, throughput, and the only way we have to know this is to create a queuing network and evaluate this mathematical model. So how to create the model? What is a queuing network? First, queuing network is composed of service centers. We start, what is a service center? Customers who belong to some population arrive at the service center. This is a service center, and we have arriving customers. The service center has one or more servers who are capable of performing the service required by customers. Here is the server. The server is the circle. Arriving customers, we put an arrow. The customers are arriving. Circle is the server. There could be one here, but there could be more servers for this service. If a customer arrives and they cannot gain access to a server, the customer must join a queue in a buffer until the server is available. So if the server is serving somebody else, they wait in line, in the queue. And when the service is complete, the customer departs, and the server selects the next customer from the buffer. So we will use, for this behavior, we will use the representation. Arrivals, an arrow, departures, an arrow, the server, with the numbers of servers and the rest of properties of servers that we will see in a couple of slides, and the queue, the buffer, with the properties of the buffer that we will see also in a couple of slides. This service center is characterized by 4 properties. I mentioned these 2 already. The arrival, how it serves the arrivals, how the arrivals wait in the queue, and the type of the arrivals. So let's talk about each of the properties. The arrival represents the jobs entering into the system. The arrival specifies how fast, how often, and which type of jobs the service center can serve. So the arrivals can come from an external source to the queue, from another service center. So when they finish their service in this service center, we connect to this other. Or from the same center through a loopback. So this is useful when we have to do some iterations in some activity. So if a system, for creating the answer to a web request, we have to ask the database 3 times, one for the images, one for some table. So we do it 3 times, and then we will depart.
What's the symbol for the circle and the box? What does it mean?
Which symbol?
The symbol that's you, yeah.
This is the server, and this is the buffer.
Okay.
So this is the same as this. So we are going to work with blocks of this: arrow, arrow, buffer, and circle. So server, queue, arrival, and departure. So server, the queue, and now we are explaining the properties of the arrivals. So the arrivals can come from outside, from some other service center, or from the same that comes back. For the arrivals, we will use the metric, the average arrival rate, so the frequency with which arrivals come, 3 per second, for instance. The second property to characterize a service center is the service. The service represents the time that a job spends being served. And we use the metric average service time or average service rate. So average service time, a job needs half a second of CPU to be served. The service rate is the the inverse. So if the job needs half a second, the service rate can be 2 jobs per second. If we work in service rate, we are working in frequencies that is in the same unit as the arrival rate. So sometimes it's easier to work always with the frequencies. And properties of the server, so the time and how many servers we have. We can have a single server, so means that there has capability to serve only one job at a time, and the waiting job will stay in queue until in the buffer until they are the jobs chosen. Or we can have more than one server, like C servers. We use the variable C for this. In this case, the service center has the capability to serve up to C jobs at a time. We have a CPU with 4 cores. The first 4 jobs can be run in parallel. The 5th, 6th, and 7th have to wait. And sometimes we may assume that we have infinite servers. So when we assume that there are always at least as many servers as there are jobs. So in this case, we can assume that each job can have a dedicated server as soon as it arrives in the center. There is no queuing in this, and the service center acts as delay. Only delay for the service time because there is no queue. When do we use the infinite server? For instance, to model the transmission times. Even if the routers don't have infinite capacity, we cannot model so accurately how we influence the global internet traffic with our requests. Like maybe it will be in the queue after some other request from somebody else. So if we don't have this modeling capacity, we say the transmission time will take 0.25 seconds in average. And we don't represent the queue, only delay. The third property that characterizes the service center is the queue. The customers who cannot receive service immediately, they wait in the queue until the server is available for them. Types of queue: finite queue and infinite queue. If it is finite, there are 2 alternative behaviors when the queue is full. The first one is if the fact that the service center is full is passed back to the arrival process. So if this service center serving all jobs and this queue becomes full, it's passed to this one. So even if this one finishes something, cannot pass and cannot serve its one. It remains blocked. An example when this happens, air traffic control. So it's the airport handling the aircraft that are landing, and some aircrafts are waiting for their turn. If the airspace has some buffer as well. So if there are so many aircrafts waiting there, the airport calls other airports and say, don't send me anybody because I don't have room for them. So the other airports, even if the aircraft has passed their zone, they keep them in their zone before passing to the other airport control area. Yeah. So when there is bad weather in some airport and the other becomes saturated or something like this, this becomes slow for a moment. The queue may be full, and so there's the other people. Even if you finish your job, don't send me anything because I cannot even keep them in queue. And the alternative behavior is like when an arrival arrives and if the queue is full, the job is lost. This happens in routers. For instance, if a router the queues are full and more incoming requests arrive, so they are discarded. So the one who has sent it will have some timeout, and the sender will realize that it has been lost. But I don't notify anybody and I don't block anybody. So these are the 2 behaviors when the queue is finite, or if the queue is so long, the buffer is so large that it never affects the behavior of jobs, we assume that it's infinite. So maybe infinite, the theoretical infinite, we can never have it because our storage is finite. But if we assume that it does not have any effect, so we will always find some spot in our memory, in our hard disk to store one more, we can assume infinite. So because the math are easier if we assume infinite than if we assume 2 to the 60. And another property of the queue is the service discipline. So people who are in the queue, how they leave the queue. First come, first serve, so the first in, first out, or like a stack, last come, first serve, or random selection, so people arrive, and it's not a queue, there is a set. It doesn't matter when you have arrived, I pick somebody randomly, or round robin, I offer a little bit to each one. Or processor sharing, that is the limit of the round robin. Or with priorities. So different jobs can come with different priority. And about this, so far we had assumed that all the jobs were the same, and the priorities mark different kind of jobs. And this, we can see this in emergency in the hospital. There are people white coat, like they can wait there, yellow coat, red coat, black coat. So even if some white coat has arrived first, it will be served before the other white coats. But if a red coat arrives, it goes first to the doctors. So, and this is how we define the population also of a service center. Ideally, the members of the population are indistinguishable from each other. But when this is not the case, we can create classes of jobs. And in each class, everybody has the same behavior. They are indistinguishable in the same class. So and different classes can differ in one or more characteristics, like the arrival rate. And say that white coat people arrive 1 every 15 minutes to the hospital. The service demand, they need 20 minutes of doctor. Execution priority, low if there is time. And red coats arrive not as often, so maybe they get a red coat twice per day, but they require more time and they have more priority. So we can, if in our service center we represent the doctors, then customers arrive with different priorities and the queue can handle this. An example of our first queuing network using a single service center. Let's consider a wireless access gateway, and we have measured it and we have seen that packets arrive at a mean rate of 125 per second, and they are buffered. And the gateway needs 2 milliseconds to transmit a packet from the input to the output. And the buffer has 13 places, including the place that is used by the packet that is being transmitted, so 12 plus 1. And if packets arrive when the buffer is full, they are lost. If I design here, YouTube, cannot see much. So a service center, I don't do it incremental because this blue pen cannot see much in the screen. So arrivals, 125 packets per second. So the lambda, the frequency, 125. The service center, there is one, and takes 2 milliseconds. So the frequency can serve up to 500 per second. And the information about the queue that we have is like, it's finite, and it has 13. So if it is open, we don't draw this last line. So I didn't say this before. If they are finite, we close the boxes, and if they are infinite, we leave it like this. Just some notation. So this, from this description, this is what we can create so far. Queuing network. This is?
Infinite or not infinite?
This is finite. 13. Yeah. So the box closes. So now let's combine several of these to create the behavior of the system, which is a queuing network. So for many systems, we can adopt a view of the system as collection of service centers with customers that are circulating. So in this case, if we have this represents the system, we see that the users arrive to this subsystem and they can go here or here. And from this subsystem, they can come here or come back here. And if they are here, they can do like this. And from here, they cycle or they leave. So it could be like web server, application server, database in the end, some subsystems. And if we can compose like this, we can also compose our service centers and create this was a service center with a queue and network of queues, a queuing network. So this represents the same as this. So if the request arrive and they come to the first one, and from the first one can go up or down. So up or down. If they go up, you can go to the last one on the right or come back to the first. So here there is some part that we haven't seen so far, and this is a characteristic of only when we combine, and we will see now. But we can come back to the first one or going to the last one. If we are in the bottom one, we can only go to the right here, and if we are in the right, we can leave or come back to the bottom. Leave or come back to the bottom. So when we combine this service center, we have a couple of properties more. Beyond the arrival, the type of service, the type of queue, and the type of population, now we have the type of the queuing network. So if it is open, closed, or mixed. If it is open, the jobs arrive from an external environment. We do this usually when we say that users from the internet arrive at a rate of 5 per second. Okay, from some context of the internet, they arrive to our system. In a closed one, we have a fixed population that remains in the system. In this case, when they finish the last operation, they come back. Fixed may be, this is the computer system of our organization, and we have 200 employees. So they use the system, but then when they have some answer, they come back to use the system. But maybe they don't use it immediately. So if they are working with the system, they receive the answer, and then they work themselves to come back to the system. And this is what it is called interactive. So when they have finished it, there is some delay. Think time of the user is called this as well. So in the example we'll see later, like if you are using the document repository of your company, there are 200 people. We interact to get the documents or to store the documents, and if you get them, then you read, or either you read or you start creating another one before submitting. So you have some think time. This is interactive. So the number of jobs is fixed, but they have some think time. They are interacting with the system and doing their own work.
Can it also be an open network? Can it be an interactive open network? No?
Then then in the open, it's assumed that they are indistinguishable. So if it is the same user that is still navigating in the same, it does not represent this. Maybe you can do some open, but with cycles. So this open means a user comes, does something, and departs. And then the next one that comes, we cannot say if it was the same one as before that has told.
It comes from like outside, then it's processed by the server, and then there's like some need of input from the user. So
Yeah.
that's like interactive time.
You could
more servers to.
you could do this like when they finish the first time, if they interact for doing so if they watch 10 pages in average, right? So you enter in some web application and some online shopping, and you click several times. So you come from the internet, and if you have the information that average you navigate through 10, you can say that when you finish, there is a probability to leave because it was the last one, or to do another iteration. So it's still open, and this would be an internal cycle in the network. So
Sign up for Facebook.
yeah,
You put like a wrong something and then
yeah, exactly, yes,
a loop.
yeah. So you could sign up, and then here you could have an alternative, success or fail. If success, you go to another one, and if you fail, you come back here, loop back. And then we can also mix. Since we can have classes of jobs and classes of population, we can create a mixed workload that exhibits both open and closed patterns. When can we, an example when we can have this, like a database that is receiving requests from the users, and there are also some batch jobs that every hour there is a batch job in the database that gets some report. So this batch would be closed. Like I'm here, I will use the database once. When I finish, I will wait for 1 hour, and then I will execute again, together with the other users that are arriving. So the fifth property that we need to characterize a queuing network, the first four were for the service centers, or for the queuing network, we need the routing, how we transmit jobs from one center to the other. There are some ways, like direct link. So this is the first arrival to the system, the completion, connecting one to one. And the alternative is the one that needs more explanation. The other ones are trivial. So when a job finishes their service in a service center, when there are several possibilities. So they go from the service center one to the second or to the third. Then we have to define some policy of the alternative. And this policy is what we call the routing. During this routing, we can also change the class of a customer. So if we had a white code customer, after when we are routing, we can say that now it changes to red. This might be useful for revisits, to know if people are in their first visit or in the second. Policies or algorithms to implement the routing. We're going to explain 3, and we will use mainly 1. So probabilistic, each path has assigned a probability of being chosen. So this was the example before. From here we can go up or down, and from here we can go back or to the right. These are the decision points. And if it is probabilistic, and here we have 2, we add a probability to going up and a probability to going to the down. And both probabilities must add up 1. So 0.5 and 0.5, or 0.9 and 0.9 and 0.1, and so on. But to be able to, when a job finishes here, probabilistically, I'm able to choose which is the next one. Could be round robin, in which the destination is chosen by the job rotates among the possible exits. So the first job goes here, the second here, the third there, the fourth down.
For the probabilistic one, does it randomly pick which one it goes according to the probability,
Yeah.
or does it finish one and then go to the other?
Random. Yeah, there's no. Maybe these ones are slower than this. So maybe here, actually we have a web server that is quite fast because it does not do a lot of work, and then the application server has to execute some algorithm. So here it might take some time, and this we can distribute round robin or probabilistically. And the third one, that ideally would be the fastest, join the shortest queue. So when a job finishes here, and it has to choose where I should go, it asks, what is the size of your queue, and what is the size of your queue, and I will join the shortest. So this is in theory. In practice, this has some problem. Can be?
By priority.
If it is how priorities are defined, if you give priority, it will always go to the higher priority, unless you are able to do dynamic priorities. Unless you can say that for some period this will have higher priority and this one will have, yeah. If you cannot change the priorities, all of them will go for.
But it's not efficient. Like only high priority go to the up one and
Yes.
only the.
Yes, this is according to the class. The routing can be according to the class. So here, everybody comes in because it's the door of the hospital, the first person that you give the card, and then you can say the important or the critical ones go in one direction and the others to the waiting room.
But it's not efficient, right? Because like imagine if you had like a few priority processes and like much more
Yeah.
less priority.
Yeah.
So like one server will be full and the
Yeah.
other one will be like having nothing.
Yeah.
So
So you can size the size, you can study how much size you need here and on the other, no, to avoid wasting. So if you think that in the priority you need few resources because there are not many requests, you can say a small room because there are never two people here. Another case that was in last year assignment is like if the login phase is done, then when the user is logged in, you can know if it is a normal user or an admin. So if it is a normal user, you can have the normal interaction with the system, and if it is an administrator, it can go to another part that has more privileges, and it's like more demilitarized zone. So in that case, there could be two different servers. What the users can do that is like very protected because it can be attacked, and another server separated in another room, what admins can do. In this case, they would arrive all classes here, and then this routing would be based on the class. If the one who logged in is an admin, goes one direction, and yeah. So let's do an example, which is part of what you can find in the assignment. You find a problem like the document repository system at our company has the following characteristics. The users connect via web to a web server, and there are 200 users in the company. The web server receives the user requests and communicates to the application server of the system. User, web server, communicates to the application server. The application server processes the document to extract some data of some structured fields and connects to the database to store it. With this information, we can create some queuing network like this. It's not complete. We don't have all the information because this is not completely defined. It has given just some info. But we can say that we have closed population, 200. It's not going to be open. It's fixed amount. First, it goes to a web server. When it finishes, it will go to an application server. When it finishes, it will go to a database, and then we'll come back. We don't have anything else. So what is going to happen with the population and with the service times and we can have more information. So with this is everything we can do. If we also have the information that when an interaction has finished, users need in average 10 minutes of work in a document before requesting a new storage, then we can add something else here. Now we know that it's the closed population of 200, and we have a delay of 600 seconds, 10 minutes. So they interact with the system and they will wait. if we also have the information that says web servers need 100 milliseconds to process a request, the application server requires half a second to process a request and has 2 computing resources, and the database requires 400 milliseconds to store the information, then we can fix the information here about the service time. So we will put, if we work with frequencies, 100 milliseconds, like 10 per second, half second is like 2 per second, and we have 2 computing resources. So the C, this is single server, this is C, servers available, and the C is equal to 2 here. And the database, 400 milliseconds, so it can compute 2.5 requests per second.
Are we supposed to do these calculations in the assignments? Do we have
Which calculations? This.
Yeah.
So, well, so far it's creating the model from this information, right? We haven't, then the question will be, what is the response time of the system? Or what is the utilization of the database? This will be the kind of performance indices. So far this is information you get and you create the model. And then when you know the math, you analyze this model and you obtain the performance results. But today we stop in modeling. The next days we will assume that we know this and we'll start applying math to know response time and throughput and utilization. Yeah, today is about just creating the motivation and creating the queuing network. Nothing about analysis. Let's increment the system with something, just to use some routing to see how we model the routing. So we have the web server, application, and database, and now the application server processes the document to extract data of structures fields. If the user requires the document to be signed, the application server connects to an authentication of signature server to sign it and then stores it in the database. So here, if the user requires, so it does not require all the time, in every execution. So some documents are signed, some documents don't need the signature. So the queuing model in this case is it interacts with the web server, then it goes to the application server, and then it might require a signature or going directly to the database. So if it requires signature, after signing it goes to the database. So with this information, this is everything we can do. And we know that we need some information here. We can complement with the routing and with this service time. So with the assignment, you will have also information like users require the signature in the 50% of documents. And the authentication signature server requires 1 second to sign the document. So in this case, the 50% of documents using probabilities is like 0.5 and 0.5. And the service rate, 1 per second, because it requires 1 second. And so in this way, you create the queuing network from the problem description. Well, this is everything for today. If we can advance something and saying that this was like a route description, but from here at the same time, you may also have like sequence diagrams or activity diagrams. Let's say this represents the same. So the user submits a document to the web server, then process document in the application server and stores the information in the database and returns. And it seems that if we have here, we can also create this structure, because so maybe from the UML, we can automatically create this structure. We know that this to be useful needs some other information, like the mu and the array, the probabilities. So we could see if there is some technique to add this information also in the UML in the beginning. So not everybody needs to know this, but if they are designers and they can represent in the UML the information that would be required, then with one click, maybe this one is created, evaluated, and return it to the user, the performance results.
What's happening to the return then? Like stored processing. There's a return. Like how is it? Why is it not showing in the model?
Yeah, well, this is a transformation decision. If the web server had done something here, not only returning, so they submit, they process the document, store the information, then the application server returns to the web server, and the web server does some operation there. Yeah, then there should be something else.
Shouldn't be a loop, no?
Very good question. Yeah. But if it is a loop, and we come back here to use the web server, the job, if we cannot distinguish from the others, it would be like the same as if it were here. And in this case, it would be again to the application server. It would not finish. If we are representing.
And you make another service that will distinguish between
Yeah, nice. We can add here another web server. But in this case, this is very good. I'm happy that you are saying this. But I have to say why not as well. In this case, they are not using the same resources. Even if we have only one web server, there could be a job executing this and another job executing this here. Well, in reality, it could not happen if we have only one server. What we could do, when it finishes here, it comes here, changing the type of user. So now it's like user iteration 2 or user in return. And this has the routine has for users first visit, go to application server. For users of class return, go out, leave the system. So in this way, very good question. Yeah. This was supposed to be answered in the fourth lesson. Yeah. Yeah, because it's when we study more the UML and we see if the UML, using directly the UML gives some benefit with respect to this. But yeah, this was the example of what happens with the returns if I have to do something here. Very good. So this is all for the first lesson, and after today I hope that you feel motivated, that knowing the performance of the system before implementing it is useful, and you know how to create a performance model in the queuing network language. So if you get a description of the system that says this goes after that, and routing probability 50%, maybe even the loop back, the time that each operation takes, the size of the queue, this, you can create a model in this queuing network language. This was the goal of today. So, thank you. Is there any question in Slack? We can hear you. No. And general, no questions. So, thank you very much for the participation to everybody. And see you on Friday. On Friday. Yeah. See you on Friday.
So like we'll have to understand the calculations by Friday. How to calculate everything. Because I skipped it.
You skipped, eh?
How to calculate like a ratio and like the
Well, so far it was given, this information.
yeah.
It was like doing the inverse, or just if they say there are two servers, you had to put the two there. So far we are not calculating so much. On Friday we will see some operational laws that do the utilization law. You have the arrival rate of one user every 2 seconds, and the demand is half a second for each user. What is the utilization of the resource?
Okay. So we're gonna do like arrival time, turnaround
Yeah.
time.
Yeah. Response time, throughput, resource utilization. And how is this closed? Let's see.
Okay, go. Thank you.
Yeah. See you.